Hello, everyone. I'm Nate Fields, Associate Editor for Modern Machine Shop, and I'll be your moderator for today's webinar, Automation for All Shops, All Sizes, All Budgets, brought to you by Okuma. In today's competitive manufacturing environment, automated technologies have transitioned from being optional enhancements to becoming an essential part of daily operations. Today's agenda covers the case for CNC automation, metrics that prove the automated competitive advantage, the importance of seamless integrations, and more. Our presenter today is Wade Anderson. Wade is a machinist by trade who started programming machine tools in 1992. His early years were spent working for companies machining large, heavy equipment components. Wade became an applications engineer for a machine tool builder, where he spent 11 years developing super abrasive aerospace and medical processes with an emphasis on 5-axis grinding. Wade joined Okuma America Corporation in 2005 as an applications engineer and moved from there to inside sales, sales engineer, and regional manager. He was recently promoted to products specialist sales manager and tech centers manager, where his diverse background enables him to help Okuma's distributors and end users go beyond their manufacturing challenges. Before we get started, just a couple of housekeeping notes. First, I want to direct your attention to the panel that's probably on the right side of your screen. You'll see a tab that says Q&A. So if you have any questions at any time during the presentation, submit them there and we'll answer as many as we can at the end. Also note that this webinar is being recorded, so if you're not able to stay for the whole thing, or if you want to refer back to it or share it with a colleague, you'll get a link to that recording via email, usually within a few hours. And with that, I'll hand it over to you, Wade.
All right, thank you. Listening to your introduction right there, all of a sudden I realize I feel very old now after listening to that opening line there. So I've been in the industry a long time, really enjoy everything about manufacturing. And I just want to say I really appreciate all of you joining me here today for this webinar. So I sit on the board of directors for our school district. And the other day, our superintendent during a board meeting, she opened up a presentation with this slide. And I kind of got lost as soon as I saw this slide because she's trying to talk about organizational changes and things that need to take place within the school district. But as soon as I saw this, my brain went automatically to, this is what we deal with every day on a daily basis, right? This is something that most machine shops, if you're an owner, a manager, or any type of leadership position within a company, you know, you've got the current position. You know, you've got two guys sitting here at a board looking at a plan, looking at an equation, and you've got your current state of affairs. You got where you currently are, what your current processes are, the problems, the opportunities, the things that you know currently. Then you have where you want to go. You've got your desired outcomes and where you want to take the company, where you want to go to. And then you have that little middle piece, which is just, you need a miracle to happen. You need something to happen here in the center. So some of what I'm going to talk through today is really part of that middle piece. How do we help companies go from where they currently are, where they know they are, their current state of affairs, to where they want to go, dealing with some of the problems that they deal with on a day-to-day basis. So two things that I know all companies have in common. I have the great fortune of working with companies really globally across the globe. And there's two threads that I always find in every conversation that everybody deals with. And the first one is the actual product that companies sell, you know, the actual product that everybody is involved with. Every machine shop, you know, one shop might be an aerospace company. They're cutting Inconel and titanium and hardened machine alloys. Another company's in medical and they're doing a different type of material. Then you get people that are into aluminum and structural and automotive, and everybody has their own niche in the marketplace. But the one thing that they're all actually selling is time. So time is what your product is, and the people who get the most out of their time wins in the end. So the first thing is time. The second thing is challenges, right? Problems or opportunities. If you're a pragmatic person, you know, a lot of time you look at things in terms of problems that you're trying to solve. You know, the real cheerful personality types talk about it in terms of opportunities. But at the end of the day, there's challenges that you have to get through to be able to move to that next step, to be able to elevate your company to where you're trying to go. You've got that challenge that you've got to be able to overcome. So what we see is a very common place in our market space in manufacturing today is the time and the people problem. You know, you see machines, the doors open, the light sitting yellow or red, the spindle's not running. And everybody knows that machine tools, if they're not cutting, if that spindle's not turning, that machine is not producing money for you. It goes from being an asset to being a liability. So a lot of what we want to talk about is how do we help that scenario? How do we help in the challenging times that we're in to help be able to bridge that skills gap or be able to just fill where the shortages are? This was an interesting slide that was given to me. A friend of mine at Fanuc Robotics actually provided this to me a while back. And it's based on a recent study where the number one concern for 82% of the CEOs in our industry all state that skills gap is a major issue that they contend with. So when you break that down, you look at lack of applicants. This was something I dealt with as we're starting this new division within Okuma and building a team. Just a lack of applicants. I remember when I first started in this industry, you fought for positions within companies. You trying to get interviews and be able to nail the interview and get hired in. That was a challenge. And today, trying to attract people to send applications in becomes a bigger challenge. I look at the workforce that is surrounded by us, even guys like myself. For years, I was always the youngest person within the company. I worked for another machine tool builder prior to my 18 years at Okuma. And I was a kid. I was a baby back then, right? And, now I look in the mirror, I've got a lot of gray in my whiskers. So this entire workforce is aging, and we've got to build that bench strength of talent to be able to backfill that. And then there's going to be jobs that are going to be the menial tasks that people don't want to be involved in. And that's an area that automation can really help be able to bridge that gap. So when we look at automated cells, we've seen over and over where automation gives you the highest percentage of utilization. So keeping that spindle running for more hours throughout the day. So this is an actual customer. This is his OEE board that sits at the end of his manufacturing shop. And he's got an automated Mac turn. So a Mac turn, that's a previous generation mill turn for Okuma. So it's the previous generation, basically, to a Multus. So anybody out there that knows that machine, it's a very complex machine. It's basically 9 axes. It's like having 2 lathes with X, Y, and Z travel and a 5-axis mill all combined into one machine. So it's a complicated machine. They do small lot sizes, constant changeover. And yet, when you look at that, that's the highest utilization in their shop. They're running an 80% spindle utilization on that machine. And that is an automated cell. That's a cell that is loaded with a robot system. It handles the changeover and things of that nature. And then as you start breaking down the rest of the shop, their numbers drop significantly. So this is a typical scenario that we see over and over with machine shops, in that what they start with from manual operated cells. And even if they think they don't have the lot sizes to be able to automate, once they get into that arena, they realize their spindle utilization goes up dramatically. And part of that scenario is because when you look at some of these statistics, in a typical 8-hour shift, even if everything is running perfectly, everything is running like you expect it to, on average, 12% of an 8-hour shift, that machine winds up sitting idle at some point. So it's waiting on an operator. An operator's at break, or an operator is spread loading 3 or 4 machines, and he's in the middle, he or she is in the middle of loading one machine when this one stops, and all of a sudden that stack light goes from green to yellow, and it's waiting on that operator. So having automation can help affect that dramatically right from the start. So anytime you're trying to implement change or move in a different direction, you always get the yeah buts, right? You get the yeah, but I can't afford big systems like that. Yeah, but I don't have the manpower to be able to do this type of work. I don't have the skill set to be able to implement. I don't have the budget to take on this type of automation. And the thing that I want people to think about, a lot of times when you think automation, a lot of the mindset in North America goes to these big integrated systems type cells. But we can help get across and find a solution for the yeah buts by starting small. I'm a firm believer in anything you take on, you really need to do that crawl, walk, and run. So many times we wind up with customers that they've got a project, they want to automate it, and instead of crawling and walking and then running, they want to go from 0 to full out sprint. And then when they get the dollar amount or the complexity of a big cell, they lose interest in it. The fear sets in and they wind up walking away from it and going down the path that they've always done, because change invites chaos, right? And it's something that you have to be able to work your way through. So starting small, starting with simple systems that are budget friendly, and then growing, helping a company be able to fine tune their processes to be ready for bigger implementations, really is the right scenario. So in today's presentation, I'm going to go through each segment of basically starting with something small, how that can be multiplied and then compounded into bigger, more complex systems. So this is going to kind of serve as the roadmap of some of the things I'm going to talk through today. The common types of machine tool tending, machine tool automation. So the first one that sometimes gets overlooked when we start talking about automation is actual control. So for us on the Okuma, we run a OSP control. It's our proprietary control. Doesn't matter what control system you're running. Everybody's got their own different front end to them, but most controls on the background, it's either for us the OSP, or you've got a FANUC back end or a Mitsubishi or whatever. But you want to make sure that you're working with a control and have the ability to have robust interfaces, and then the system monitoring, which I'm going to talk more in depth here in just a little bit. Then we're going to talk a little bit about bar feeders and making sure that we're getting the most out of bar feeders. That's really our entryway into automation. Almost every shop that you walk into, they've got a bar feeder, right? They're already in this automation space, but are we getting the most out of it? Then robotics. I would argue that as soon as you say machine tool tending or machine tool automation, this is where most people's mindset goes. Robots wind up being at the forefront of your thought process when you're talking about automation on machine tools. So I'm going to go through a couple of scenarios on, again, how do we start small and how can that go from, the old cliche of think big, start small, scale quickly in that type of a scenario. Then gantries. I'm a big fan of gantry loaders. I want to talk through a little bit of that, where you use them, how you use them, implement them, that kind of thing. Pallet pools. How do we take machine tools from being a standalone machine or maybe a 2-pallet APC machine like most of your horizontals, some of your verticals have, then expand that capacity in a small amount of real estate. And then lastly, we'll touch on FMS systems and really going into big full-scale type automation with FMS systems, companies like Fastums and people like that. So prior to automating, you have to have complete control of all your variables. This is one of the most important steps. I've talked about this a couple of times in different podcasts and things like that. But if you rewind the clock to IMTS, about 2016 timeframe at IMTS in Chicago, everybody was bringing robots to the show. Everybody was jumping into this automation bandwagon. And the main question that everybody was after is, how do I get a robot connected to a machine? And how do I get it putting parts in a chuck or loading a table, that kind of thing? And that's really the easy part. Putting a robot on a machine, that's the easy part of that equation. The hard part is, how do you get the utilization out of that cell that you're expecting? And a lot of that comes down to the variables. So when you look at IMTS 2022, this past IMTS, almost every conversation I had circled around, okay, I've implemented a robot, but now how do I get this thing to run 24 hours a day, 7 days a week, the way that I thought I would when I first incorporated it? So some of the requirements that you have to be able to automate a system is really comes around a stable process. You cannot automate a bad process. Automation is going to help you make a lot of parts, and automation will make parts really good, or it can make parts really bad, or it can sit idle while you're waiting on something to get fixed, repaired, that kind of thing. So you got to have your process stable to begin with. So I'm not going to read through all the bullet points. You can read faster than I can talk here. But being able to make sure that you've got a tool strategy, that you're measuring your tool life. And most importantly, do you have a method of stopping a tool from breaking. This is where I would insert guys like Karen Engineering, their T-Max software, where you're actually measuring the real horsepower draw, and it's got the capability of stopping that cut before the tool breaks, calling up a redundant tool, and finishing on in that cut. Those are some of the strategies that you need to have in place before you ever look at implementing. All the way down to coolant. This is one of the things that is overlooked so many times, and we come in on the back end and have these conversations after a machine or a cell has been on a customer's floor for a year, 2 years, and they're experiencing problems. Are you using the right coolant for your application? I know of coolants, for an example, if you're machining aluminum, you wind up with all the aluminum fines. There's coolant out there that's got certain properties that will help that sink, to help with the filtration process, things of that nature. Are you just using what's cheapest on the shelf, or using the right coolant for the right process? When I talk about coolant, a lot of times we want to look at what are the gotchas, what are the areas that could be easily overlooked that could wind up shutting down a cell, and again, not allow you to get the utilization that you're expecting. So this is a picture from a customer's shop. Great coolant flushing. You look at that top picture, you've got a lot of really good volume. You've got good amount of coolant coming in, washing different areas of the covers. But then if you get down and get the camera a little bit lower, you see some problem areas, right? You see some areas that when you see chips collecting in certain pockets, there's nooks and crannies that standard coolant nozzle that a lot of times will come on machines, they weren't aimed in the right place, or they don't have a nozzle where your specific cutting process is throwing chips. So a lot of times you really want to look at your coolant system and actually fine tune that for your specific process. There might be coolant nozzles that are aiming in areas where chips are not hitting at all. Well, you can plug that coolant nozzle off and tap in and add another coolant nozzle in an area where you're seeing problems like this. Because if you allow chips to build up in areas like that, eventually that axis is going to come back. It's going to crunch some of those chips. It's going to get under a way cover, and that creates an opening. As soon as you get an opening, more and more, it's going to become a compound effect where all of a sudden you're going to wind up with a down machine because of something that could have been prevented early on with proper tuning of the process. If you walk behind your machine tool and you look at your chip conveyor, and your coolant tank and chip conveyor looks like this, I promise you, you are not going to be happy with any type of automation that goes onto that machine. Things like this have to be solved before you start looking at implementing robotics or automation. So in this particular example, this is a customer that's machining aluminum at high volumes, high rates of material removal rate. And a study was done. One of our partner companies, NP Systems, they specialize in high pressure coolant and coolant filtration, things of that nature. They actually sent in an engineer to watch a customer at a very similar type scenario to this, to watch it run for days on end. And what they noticed was, first shift, the operator would come in. He's kind of the guru guy, the setup guy. He would come in and he would top off all the levels. He would top off all the way lube, all the coolant, check the coolant concentration, get the water adjusted right, fill the tank, all that kind of thing. And then as the machine is running, he's off. Second shift starts coming in. The machine is running completely unattended. And then about halfway through second shift, the water starts to evaporate from heat, from boiling out during the machine process, different things. But the water starts to evaporate. Coolant concentration gets thicker. It gets heavier. And before long, it starts foaming. And all this aluminum wound up floating on top of the foam that was developing during the middle of third shift. So through the night on third shift, while these things were running unattended, this foam is just crawling out across the coolant tank and then depositing chips into clean coolant areas, things of that nature, where you don't want chips to be. So in a situation like this, part of the automation that needed to go in place was a coolant automation to be able to maintain that through the night when the operators weren't there. But it's scenarios like this that need to be fixed before you start looking at implementing things. So when I talked about system monitoring, this is an area where we can put sensors around a lot of different areas of the machine. And again, your specific needs might be a little bit different. But coolant concentration, coolant pressure, and flow, that's an easy one. That's low-hanging fruit. But you go all the way down to start thinking outside the box and looking at what shut your machine down, and is there a way to solve that? So I'll give you another example that we've witnessed, where a customer had most of today's modern spindles run an air oil mist lubrication system. So it runs a specific type of oil that mixes with air that goes into the bearings of the spindle. They had a situation where the wrong type of oil, like a Whalube oil or something like that, got mistakenly put into the spindle lubrication system. Well, the two oils reacted to each other and it congealed. So all of a sudden, the spindle wasn't getting the air oil mist lubrication that it needed, and eventually shut the machine down. Well, there's ways we can solve that, from simple color coding to barcode scanning to even going as far as having RFID type chips. There's ways that you can look at, okay, what was the problem? And then how do we solve that problem? So these are things we want to be thinking about. Again, how do we control that entire process? Anytime you have a scenario where you have an operator that has been used regularly to be able to allow parts to load, for an example, I go back to when I was a machinist right out of high school. I worked for a company called Holset. They did bearing housings. So we would machine on a lathe, we would machine the bearing housing, and then it would flip over into a fixture that went into a machining center. Well, to be able to put that part on the fixture, we would have to wash it off and then literally take our hand and wipe around the seating surface to make sure we didn't wind up with a stray chip that the flange that had already been machined isn't going to sit on and create indentation on that part. Well, if you're going to automate that, that type of stuff can't be there. So you got to think about that in terms of, can I build that into my work holding or into my fixtures where I have coolant or chip air blow to make sure that all of my seating surfaces are going to be clean when that part is presented. So that's part of the strategy that needs to go into your fixtures and work holding. If you're using types of machines like a horizontal, for an example, where you're loading parts where now gravity is not working in your favor, thinking about strategies like having spring retentions so that the robot is kind of snapping the part into place with a spring retention and allow the robot to get out of the way while the hydraulic hands come in to clamp the part. Those are some of the considerations you want to be thinking about in terms of the work holding strategy, things of that nature. So when I look at strategy, I like to talk about the process flow. And this was a slide that's been put together years ago. I've used it probably for 5 or 6 years now. I actually think a gentleman named Jeff Estes, who used to run our Partners and Think, he was a longtime Okuma employee. I think there was a slide he actually put together, and I've had so many customers comment on it. I usually keep it in almost any slide deck that I'm working on because it really helps paint the picture of what does your process flow look like. And that's going to dictate a lot of how are you going to implement automation into that scenario. So there's times when a conventional process, depending on what your part volume is, a conventional process of having multiple machines is going to create parts faster. But then there's other times you could look at a multifunction machine. For our case, it would be a multi-style machine, or perhaps a 5-axis machine with turning capabilities, things like that, where that's going to be a better process. And a lot of times there's simple math that can be done that's going to help you decide which process do I want to go down. Do I want to do 2 lathes in a machining center, or do I want to go to a multifunction type scenario? So obviously your times are going to be different, but you need to look at what your setup time is compared to the takt time for your parts. And at the end of the day, your setup time over run time gives you what your break even point is going to be. So in this given scenario, and again, your numbers are going to be different, but just for an example, this given scenario, if I'm running 41 parts or more, then my conventional process is going to be the fastest way to machine parts. But if I'm doing below 40 parts, if I'm doing lot sizes of 10 or 20, now a multifunction machine is going to be the fastest way to make parts because of the changeover time that's involved. So those are things that you want to look at to decide what your strategy is going to be, because once you dictate how your part flow looks, then that's going to lead us towards, are we robot loading? Are we gantry loading? Are we looking at FMS systems, things of that nature? So start small, start simple. I want to go through from simple automation and then kind of work our way up. So hopefully everybody's familiar with the KISS principle. Keep it simple, as my wife likes to say, keep it simple, sweetie. So that's something that I always look at when we start looking at processes. How do we start simple and then expand and grow on that? So bar feeders, parts catchers, unloading devices, that's really your entry level platform. So we can take a bar feeder, put it on a machine. When you're looking at the machine tool side, you need a parts catcher to be able to extrapolate the parts that you're bar feeding in, or some type of an unloader device. But the thing I want to challenge people to look at is, are you getting the most out of your bar feeder, out of the process that you're using? Are you getting the most out of that? And where I come from on that is, a lot of times we look at the amount of changeovers that people are doing and the amount of time that it takes to do a changeover, and the manpower, the dollar amount that's put into it from human resources. And if we can look at bar feeders and the spindle diameter, and we maximize the size of our bar and then get the most amount of parts out of that same diameter. So we use common diameter, common part size, and get the most amount of parts out of that. And then are we automating the unloading side of it? So in this scenario, you can see there's a bar feeder, is a edge bar feeder coming in on the main spindle. And then you have an edge extractor pulling parts out of the sub spindle. So look at scenarios like that. Are there things that we can do to get parts out? And again, taking that human resource, the labor component, out of that part manufacturing side. Unloader devices is something we do a lot on. Primarily our high volume machines like LT. For us, it's our LT, where we've got multiple turrets, multiple spindles, or our multifunction machines. So a lot of times these are used for parts that are a little too heavy or too big to go into a normal parts catcher. So we've got unloading devices that we can look at. Again, this is kitted, integrated from the OEM machine tool builder, that is easy to implement, easy to integrate. Then from here, we step into our pre-engineered robotic systems. So pre-engineered robot loaders, and really, where's the starting point for robotic systems? A couple of scenarios I'm going to talk through between industrial robots and then the collaborative robots. So for us, we have a system called a load and go, or an Okuma robot loader, as I'm getting tongue-tied. And this is a kitted, pre-engineered cell that comes in. We've got a couple of different scenarios. What I have pictured here is a drawer system. Most of the companies that are in this space that are building pre-engineered type robots have a shelf or a drawer system of some configuration. In this example, you can see the robot is pulling from the machine tool side. It opens the drawer, pulls the parts, loads, unloads the machine from that side. The operator would be on the back side of the cell and putting in the raw material. You could take that a step further and have a collaborative robot loading parts from a bin into the drawers, things of that nature, to kind of step that up one notch. But these systems use an area scanner, so it simplifies the guarding. So these pre-engineered systems come in with all the guarding needed to meet all the safety requirements. And then the area sensor puts a perimeter around it, so that as you walk into that machine, when you get to a certain range, the robot slows down. And then if you get too close, it triggers it and it stops the robot altogether until the operator or the person gets out of that cell and restarts it. So these are great systems. Again, they come in pre-engineered. All of the motion is pre-taught, so you don't need a robot programmer on staff to be able to implement these. The software to program and load them is very simplified. It's a conversational type window where it just asks a series of questions. Are you grabbing the part by the ID? Or are you grabbing the part by the OD? Are you grabbing two parts at once or only one? And it just steps you through a very simple, user-friendly graphical user interface that makes it so you don't need somebody that's got a specialized robotic skill to be able to put these in the manufacturing environment and get them implemented and up and running quickly. From here, we step into the collaborative space. This is an area that we see growing quite a bit. There's a lot of interest in this, and primarily from people who have that do-it-yourself type desire. You know, people who want to bring them in, implement it themselves, or have a simplified unit that doesn't have guarding. In this scenario that you see pictured here, we produce a collaborative robot cart, and it's meant to be redeployed to different machines. So it runs a simplified robotic interface, and it needs a power drop, and you can unplug the system, roll it from one machine, and roll it down to another. Fanuc, this is a Fanuc CRX collaborative robot. It has a great little 2D vision system that looks at I'm going to call it a QR code. It's really like a grid pattern that you put on the door or on the side of the machine. And when you bring that up, it'll take a picture of that to recalibrate itself to where your machine center lines are. So we can load up multiple machines in the software to be able to make it simple to be able to move the cart from one machine to the next and re-implement it. So if you have a job that you need to run overnight on one machine, and then the next day you come in, you've got a different job you want to run overnight, you could actually move that system and re-implement it. Most of these collaborative type robots, something that's common that you're going to see throughout that space, is they all run a very simplified programming system, more kind of modern to what we're used to versus the conventional days we're used to do all the teach points. So this is drag and drop type icons. From Okuma standpoint, we have a user-friendly interface that is more of that conversational type window that you saw on the previous industrial robot pre-kitted cell. So this is something that is a growing area that we're anxious to see kind of where this space goes. I actually see the collaborative side for me personally as being able to be used in areas outside of just tending the machine tool. What are the non-value added things that a collaborative robot could do, and let the industrial robot that's got a little more speed, a little more payload capacity, things like that, tend the machine tool, but perhaps this is doing the palletizing or tool changes, things of that nature. Then from here, I want to touch on our Armoroid and Standroid. These are integrated robots that come as part of the machine tool from the OEM. So what you'll notice here on the picture on the left, this is what we call our Armoroid. This is an Okuma built robot that is mounted above the headstock of a lathe. And what's different about that is that robot actually lives inside the enclosure in the work environment of the machine. And I'll show you some things that gives us some added value from the machining process itself. Where the Standroid, that is a traditional, that's a Yaskawa robot. You can see the blue robot through the window. That's a traditional robot, but it's running a different type of software that is integrated into our machine control. And again, it comes in completely kitted from Okuma. And it uses a conversational type dialogue screen where you're basically telling the robot where you want to grab the part. So if you've got a part that's got a flange on one end or something where your weight's going to be off, you're going to tell it where on the part you want to grab. You give it some basic parameters, but then it looks at our collision avoidance software and it determines its own motion path to take the part from outside to inside the work environment. So the picture on the top kind of represents the traditional way of seeing your traditional robot programmer going in, picking parts up, and then teaching points along a path of how you want the robot to go and get into the machine. Where the picture on the bottom, that is using what we call our robot Navi, our self-programming system, where it's looking at the collision avoidance software and it creates its own path. So every time it picks a part up, takes a part in and out of the machine, it's looking at the virtual environment and then programming its own motion path to get in and out of that machine tool. So that helps us in a couple of scenarios. It'll help highlight collision areas that you may or may not see when you're initially setting it up. And then again, it takes the need of having a robot programmer on staff out of the equation. These come in completely kitted up and simple software that anybody can use at that point. So here you can see this is an Armoroid, and you can see how it reaches outside the machine and pulls the parts into the machine. And then the drawer up at the top has 3 different end effectors that can be utilized. So it'll change out the different end effectors depending on the type of work that is being done. So a couple of end effectors that it comes with, obviously, is the part loading, the gripper hand to be able to get the parts in and out. It has a work support that can be used basically as a follow or a steady rest. It's really a damping tool if you're doing shaft work, things of that nature. And then a coolant nozzle, and that can be incorporated into the gripping hand itself. And the neat thing about that is it can follow the cut while the cut is taking place to help from a chip management standpoint, or it can be used to actually clean the machine and hit some of those trouble areas inside the machine enclosure that maybe your shower coolant's not hitting and things of that nature. So it gives you some added value to the system itself that you can't do with a robot that's sitting outside of the machine tool. So from there, we look at going from the small pre-engineered type stuff. You can take that same type of philosophy and then grow that into your full-blown custom automation. So this is a scenario where you can see one robot loading two machines, but then there's multiple other robots doing other value-added features to that process. The thing that I find very interesting about this setup, this was done by Gosser Automation, who's our sole robotic integrator. They have gone through and taken a part that is a very, very simple part. This is just a tube that an OD is being cut on, but they've automated all of the non-value added steps to that manufacturing process. So all the pre-work, getting the part ready to go into the machine, all the way down to the inspection, the measuring, and the palletizing is all done through automation. And one of the things that I really like that they've done in this cell that we try to leverage a lot when we're looking at automation is loading through the top of the machine. So you notice the machine front and back, and the robot is sitting over the top. And it's got what we call a moon roof on top of the machine where the robot comes down. The advantage to that is it allows that whole front of that machine tool to be open to the operator. So they've got access at any time they want to come up, look at the control, or when it comes time to change tools out. In this scenario, this is such a simple cut. They're only using one insert to make the entire part, and they're using a 12-station turret. So they've got 12 redundant tools that they can pull into the mix at any given time. So a really creative way of using automation for a simple part, but getting a lot of added value out of that. From here, let's talk more about high speed and high volume applications. This is where we see our gantry loaders really come into play primarily. So gantries are 2 to 3 axis linear motion type robotic systems where we are loading parts from a stocker table into the machine and then going to outbound processes. So these gantries can be configured to do shaft work or chucker work, depending on the type of work that you're doing. We can incorporate them. We have a series of machines that come with the gantry loader integrated as part of the machine tool, or we can have them as standalone systems. So what you see pictured here, basically with their own feet, that you would put machines underneath of it so they could be field retrofitted. So depending on what your needs are, there's different ways that we can approach it. One of the key features about gantries that you'll notice is just the speed. I love this video to be able to show the speed of loading and unloading parts, getting them down to other downstream processes very quickly. So in this scenario, you can see it did an Op10. It's putting it up in a turnover station where it's flipping the part over for the Op20 presentation. And then from Op20, it'll take it and put it on an outbound conveyor. Here it's doing a part inspection. So it's getting 100% post-process gauging on every part. And that can be expanded on depending on what your needs are. So this is a version just to show you a little different style of machine. This is one of our LTs. You can see it's got 3 turrets, 2 spindles. So it's doing an Op10 load. It's picking off to do the Op20 operation. While the cut is taking place, that gantry can come in and load Op10. So again, really maximizing your spindle utilization out of that machine. We have several different stocker table configurations that are standard. We also work with third-party companies who build custom stockers or pitch feed conveyors for shaft work, things of that nature. So these come in different standard configurations, but they can also be customized depending on what your individual needs are. And then just to give an idea of what can be done with a gantry outside of just the machine tending side. So much of what we talk about, we think about things in certain windows, and we think of the gantries loading and unloading parts, but we can incorporate blow off stations, part inspection, gauging, things of that nature. So that beam could be expanded and other types of downstream operations can be done to it. And again, adding more value to that automation system. And then we want to think about how can you combine different types of automation together to get the most out of it. So here's a scenario where we have an edge bar feeder feeding one of our LT style machine, or actually I think it's a Multus machine. So an edge bar feeder feeding it. And then there's a gantry overhead. This is a gantry that is picking a shaft part up after the machining process and then sending it down through an outbound conveyance system to other downstream processes. So here you're combining bar feeding automation with a gantry automation. Now, if you're doing chucker work, that could easily be a load and go system, unloading parts into a drawer cell and using it as an unloader versus a loader, things of that nature. So depending on what your specific needs are, there's a lot of opportunities we can look at. How do we combine multiple levels of automation to get the final product that you're looking for? I'll move from kind of the turning operations into the machining center side and talk a little bit about pallet pools. I'm a huge fan of horizontal machining centers. I've talked about that for years, how when I first started out machining, the very first machine I ever ran from a machining center standpoint was a horizontal. So my brain, when I look at parts, a lot of times I automatically think in terms of horizontals because I'm looking at how am I stacking parts up, working my way around tombstones, things of that nature. And horizontals are great for automation because they have a 2 APC already built into it. So you have some automation already built into the platform. And then by adding a pallet pool system, we can expand that from a 2 APC to a 6, 10, or a 12 APC very easily. And these can be field retrofitted. So it's a great way to take a standalone machine and add automation to it. Our 5-axis machines, the machine that you see up in the top left picture, that's a 5-axis machine. That was a standalone machining center. And the way our trunnions are configured, they turn to and from, in this scenario, basically to and from the operator, so we can load the pallet pool in the back of the machine. So the operator still has complete full access to the front of the machine, again, to be able to look at anything he needs to do, check tools, look at the control, whatever. He's got full access to the front of the machine. So it's a beautiful way of automating 5-axis machines. And then to step that up a level, we go from a single level pallet pool system, which is very budget friendly, to a tower or a multi-level type pallet system. So here we typically see 12, 18, or 24 pallets that get added to the system, depending on the machine and what the configuration looks like. So in a horizontal machining center, the pallet pool, the tower type system sits to the front of the machine, just as the single level system would. And in this scenario, it's the same type of operation, only you have an elevator to be able to pick up pallets basically off multiple levels. And then this can also be incorporated into our 5-axis machines. Again, the trunnion is configured in a way that it makes side loading very nice to be able to feed into the side of the machine. And it's a great way, I love this picture because it's a great way you can see a lot of density to your manufacturing process. This is showing a 18 pallet system, but using pyramid fixtures where you're getting 3 to 4 parts per pallet. So the number of parts that you're putting into the system goes through the roof at that point. And then from here, we can look at other systems. I'm a big fan. I do a lot with a company called Aroa. They're also a private label automation builder for some other machine tool suppliers. They make beautiful, very compact systems, especially for our smaller 5-axis machines. This was a machine that went to IMTS this past year, has an Aroa, what's called a Compact 80, that has 12 pallets in the system and a little robot mechanism you can see in the CAD floor layout in the center that's picking off either a rotary or a flat shelf on either end of the system and then feeding into the side of the machine. one of the things that's nice about these compact 80 systems is the way that the robot arm comes out. We can load machines left to right. So we can actually put two machines on one robot system that way. They also make these systems with a linear rail. Again, as we start expanding and looking, how do we start small and then scale up? They make a system like this that's on a linear rail system. So you could add up to 12 machines on that same linear rail, again, using one robot and adding a lot of automation to that type of a system. So as we look at single machine options, there's a couple of different configurations. Obviously, the tower type pallet pool system that we talked about. Then you jump into what's known as a FMS system, or a flexible manufacturing system. So a container system is one machine and one container of pallets. This usually is going to range from 10 to 12 pallets, depending on the type of configuration. But then you can expand these container systems up to 3 times to get 3 machines and one loading system out of it. So again, you can increase your spindle utilization, get more machines onto one type of a system. And then as you, again, start small and expand, depending on what your processes are, these systems can be very large, very extravagant. We work with a company called Fastems. They're really big in this FMS type space. And they make a FMS system that is completely modular, that can grow depending on the size of your shop, and continue to add machines to it. So I recently had the opportunity to go to Germany and visit a customer that has 2 plants and a gangway over the top, and the entire plant is run off FMS systems with a central tool storage. So the central tool storage has all of the tools for their entire manufacturing plant. And then they had a robot on a rail that went in between the 2 plants that would take tools from one central storage and then park it in a staging area to feed the other manufacturing plant. And the beauty of that is it made him rethink the size of tool changers. For years, it was always known that if you're going to do automation, you want to buy the biggest tool changer that you could put on a machining center. Well, having a central tool storage makes you rethink that, because now I can get away with smaller real estate, less expensive machine with a smaller tool changer, and let that central tool storage center be my hive where all my tools go in that I'm feeding my manufacturing plant with. So again, it kind of causes you to think a little bit differently on what can we do to maximize our manufacturing space. And then other processes could be added to a system like this. Here you can see in the picture a deburring cell. You could have wash stations, something kind of going, again, a little bit outside of the box from, I think, what most people think about is not just machining centers. We can have an FMS system, and instead of having a row of horizontals or 5-axis machines tied to it, we could have a robot cell tied to that, where your FMS system is actually feeding parts that the robot is taking and then feeding 1 or 2 lays into a system. So it really opens up the level of creativity that you can get, depending, again, what your needs are, what you're trying to accomplish. So systems like this, you could get really creative in having a FMS system load from one end, have finished parts going back into the FMS system. Or if something, the FMS is down or something happened, you could still bring carts in manually into the other side and keep that cell up and running. And again, really maximizing your usage of the type of work you're doing. Combining other types of automation, that could also be a bar feed application on one machine where you're unloading parts and then sending that into the FMS for part storage and things of that nature. So this is just to kind of go back full circle to one of my opening slides on the type of automation that can be done, starting really small and then going really big. So if you're a company that's already in that walk or run phase and thinking, what's the next level? We can tie in Cardex systems, central tool storage, multiple machines. This is a representation of 13 of our vertical machining centers, all tied together with a central tool storage system and a Cardex system where all the parts are stored. So it's really thinking about where are you currently and where are you trying to go, and what tools can we put in place to get you there. So in closing, I always like to go back to different acronyms, if you will. SPEC is one that is easy for me to keep in mind, and that's seize the data. Understand what stopped your machine from running. Why did that spindle stop? And get rid of the yeah buts. We've got a lot of digital tools that can be used to measure your OEEs and try to help from a digital standpoint capture why your spindle stopped. But don't let that be an excuse. Don't say, I can't afford it. We don't have people to implement it. Having a whiteboard and a Sharpie marker will get the ball rolling on capturing the data on what do you need to do to move your shop to the next level. And then you prioritize what your needs are for your individual shop. You don't want to come up with a list of 80 things and then try to attack all 80 of them. Come up with your list of 50, 80, whatever that number comes out to be, and then pick the top three. Pick the top three that's going to move the needle. Put all your focus and energy on executing to solve those 2 or 3 items, then celebrate those wins, motivate your team to move on to the next level. So that's all I've got for you today. That kind of wraps up my hour. So I'm going to turn it back over to our friends here for any kind of Q&A we have.
All right, thanks, Wade. It does look like we have a couple of questions, so I'll go ahead and get started. First up, I see YouTube videos of people integrating robots without factory interfaces, just wiring into the back of the control. Is that acceptable?
From an OEM perspective, no. That there's some dangers to that you got to be careful of. I think one important thing is anytime you modify a machine, you have just taken over all the responsibility from a safety aspect. So the machines, when they come out, it doesn't matter whose machine it is, when they come out, they are built to be in compliance with all the different safety regulations for whatever country they're in. Anytime you go in and you change wiring, you have just made that null and void and you took over that responsibility. So that's just one thing to think about. Other considerations, something you need to think about in terms like door opening. I've got a friend that works at a shop down near Charleston, South Carolina, and they automated a machine using a collaborative robot, and they were using the robot to open the door, which I'm a fan of. If you can find ways to use the robot in creative ways and make your investment cheaper from auto doors and things like that, go for it. But something they didn't think about, the way the door was opening, the robot was basically putting almost like a paddle on the side of the door and sliding it open. And it was almost like a radius type move. So as it was sliding the door open, it just would come off that, go over, pick up the part, and then go to enter the machine. Well, it was moving the door, and then the door was actually coming back, and the robot was turning. Whoop, as I ripped my earphone out of my own ear, the robot was coming back around to load the machine, and the door had slid back and hit it. So there was no safety checks. And that's a lot of what goes into your robot interfaces are all these signals to check, is everything clear? Is the chuck open? Is there a part present in the table? Things of that nature. So those are things that I always recommend having a good, robust robot interface that's going to do all those safety checks.
For sure. And then next up, early in the presentation, you mentioned coolant concentration. Do you know of companies that handle refilling automatically?
I do. There's one customer or one company in particular that a couple of our customers have used. It's a company called FlexCool. I personally have not used them. I don't have any personal contacts with them. But that's one that I know some customers of ours have used. So I think if you just go in, a Google search and type in CNC coolant automation, I think Blaser has their own system that does something similar to that. So those would be two that I could throw out just off the top of my head.
Got it. Next up, I'm working on implementing our own automation and tying in a gauge station and part marker. Are there off-the-shelf software packages that will help me integrate the communication between all the different devices?
Certainly. One, and we leverage this guy a lot, or this company a lot. I always say the guy, but Rob Karen owns a company called Karen Engineering. They're really big in the industrial manufacturing space. Karen Engineering, they've got a product out called, I think it's Me Connect or My Connect. It's MI and then Connect. And that's like a central hub, basically. So I got to get a little walkthrough of it at EMO. I'm not an expert on it, but definitely reach out to Karen Engineering. But it's a central hub that's kind of the software command center that handles all of the communication to all the peripheral devices. So it becomes kind of the driver of the software system and will handle all the communication protocols to different devices. So that would definitely be one to check out.
Awesome. Next up, one problem that I've seen is that there is a fine tuning of the CNC program for the first part that is machined. It sometimes requires a lot of time to set it or to get it ready for production. How can this problem be solved on automation systems?
So digital twin, doing work on your CAM system, digital twin type work. We have a system called 3D Virtual Monitor, which is a digital representation of the machine tool. That will help take out, because a lot of times what you're involved with is understanding your tool length, clearances, making sure that you're not running into clamps, things of that nature. That's where your digital twin or your 3D virtual monitor type software will help you be able to see that kind of stuff up front. So that's one aspect of it, is making sure you're using the digital tools that you can to be able to take some of that work and get it done up front before it goes to the machine tool. But I've been asked before. I had an aerospace company ask me I won't go into details on the exact process, basically a very complicated 5-axis part, and they wanted it all done with no manpower. And right now, the way technology is today, I have a hard time believing that scenario can be done. I mentioned the company that I got to visit in Germany, and he is by far the most successful automated cell I've ever seen in my life. It's a pretty amazing system, but he has standardized all of his machine tools to one platform, and it's the same pallet, and all of his machines are calibrated within 3 microns. And he takes one machine out of that cell, and that's his setup machine. So he has his setup guy that goes in, and they do all the prototype, all the prove out work on that one machine. And then once they have that, then that goes into the system. And from that point on, it can be manufactured on any machine in their entire manufacturing plant. But they are still, and that's, again, one of the most high-tech companies I've ever seen out of all the thousands of shops I've been to. But they still have an operator that is doing that first initial part run, dialing it in and making sure it's right before it goes into full automation.
Got it. Next up, are there any systems available to do both pallet pool style and small parts handling, similar to a load and go type of setup?
Yes, we've got a couple of scenarios depending, and I'd almost like to see a picture of what you're thinking, but based on what you described, one of our partner companies that we work, actually 2 of them that we work with, both Aroa and Fastums, they make a system very similar. So Fastums, if you look at the pallet pool, actually, if I can back my slide up, I hope I'm not breaking any rules here. If you look at this pallet pool system, they make this with a linear track that uses this same elevator here that you see in the center, and then it has some linear storage. So now, instead of it being tied to one machine, that elevator runs on a track where you can have multiple machines, and you could have multiple types of machines, a horizontal mill and a 5-axis mill, for an example. Aroa does the same type of scenario, a very similar scenario. So in this picture, you can see we've got an MU4000 and an Aroa Compact 80. They make a system, an ERL, I believe is the terminology for it. But again, very modular type system that could be on a track. And then you can have multiple rotary racks or multiple shelf racks, linear type racks that go into it, so that you can maximize the type of parts that go in. So these could be very small parts that fit in the palm of your hand, or they've got a multiple clamping mechanism, or you can move in full size, like bigger pallets that you've got a shunt vise on, or things of that nature. So I don't know if that's the scenario you were asking, but that's kind of where my head went when you asked that. So
Yeah, sure. I think we've got time for one more question. So this one says, to get started with simple machine load slash unload, would you recommend working with a third party company, or can it be managed with a good CNC programming and manufacturing engineering team?
So if it's simple load unload of fairly simple parts, that can be done basically through our distributors and our automation groups. So if I go back to our load and go type system here, this is something that comes in. Either us or Geiger sends people in to actually do the install. So in general, we would see a system like this come in and within 4 to 5 days be up and running parts on your production floor. And other than the initial install of getting the system in, lag down, getting the center line of the work holding figured out. Um, Other than that, then your programmers, you're going to very easily be able to work your way through this type of software. You'll get some upfront training, and you don't need a robot or an integrator on staff to be able to run a system like this.
Got it. I think that's all we've got time for. So I guess we'll go ahead and end it here. Thank you, Wade. I really appreciate it. And I also want to thank Okuma for making this webinar possible. And thank you to everyone for listening in. You should receive an email with a link to the recording within the next few hours. So thanks everyone for joining, and enjoy the rest of your day.
All right. Thanks, everybody.